Well, a warm welcome to everyone, and thank you for joining this webinar about evaporative cooling and humidification in data centers and telecommunications applications. My name is Dave Marshall-George, and I'm the UK and Ireland Sales Director for Condair. And presenting today is William Trong, who will introduce himself shortly. We've over 1,000 people on the webinar today from 55 different countries, so everybody will be on mute. But if you do have any questions, please submit them using the text question function in the control panel. I'll answer some questions as we go, but when the presentation is finished in around 50 minutes, I'll be taking some of the most popular questions and posing them to William. I'd also like to draw your attention to the documents available for download in the control panel. There's a presentation in PDF format and an electronic copy of the psychrometric chart, both really useful documents. So with that, I'd like to hand over to our expert, William, who's going to be delivering the presentation today. Hi, William.
Perfect. Thanks, Dave. Again, just want to thank everyone for taking time out of their busy schedules to join us for the webinar today. My name is William Trong. I'll be the presenter for today. I'm a business development manager here at Condair on our Evaporative Technologies team. So with that, we'll jump right into the webinar here. So just a quick introduction to Condair for those of you that aren't familiar with who we are. We are a leading manufacturer and solutions provider for humidification and evaporative cooling systems. This includes all your traditional isothermal steam humidification systems, as well as a wide range of evaporative and adiabatic systems, a few of which we'll talk about today. We're a global organization. We've got multiple distribution partners, sales offices, and production sites located throughout the world here. So with that, we'll jump right in. So the learning objectives for today will cover three main sections. We'll start with delivering the ASHRAE window and how evaporative technologies can support those. And then we'll look at a few of the case studies as well in terms of each of these different strategies and how you can apply evaporative technologies and what's available in the market today. So I'll turn my camera off quickly here, and we will get started. So I'd like to start off with an introduction to the ASHRAE environmental envelopes and ranges for air-cooled equipment. So for those of you that aren't familiar with ASHRAE, it is the American Society of Heating, Refrigeration, Air Conditioning Engineers. Now, for those of you that aren't in America, I know there's a lot of you from the rest of the world here. Although American is in the name, they are a global organization or association with over 50,000 members and more than 130 countries representing it. So a very well represented association. And in this section, we'll cover the ASHRAE operating ranges, the physics of evaporative cooling, as well as the conditions where evaporative cooling can potentially be used. Now, when we talk about the environmental ranges, we'll refer to the recommended range and the allowable range. So just a couple of definitions here just to start. The recommended range is the most important range really for data center designers and operators, and it's where the servers are going to operate for the majority of hours out of the year. Now, the recommended range was chosen based on several factors, primarily the reliability of IT equipment, power consumption, as well as to provide a buffer for potential excursions before reaching the allowable limits of the IT equipment. Now, the allowable range is where the ITE manufacturers test their equipment to verify full operation. However, it's important to note here that this doesn't mean that there's not going to be any impact on the IT equipment. So although the equipment may function at the extremes of the allowable range, it may have an impact on the performance and the reliability of the IT equipment itself. So the key takeaway on this slide is that the IT equipment should operate within the recommended range for the majority of the year, and the allowable ranges were specifically created to allow for excursions that are not outside the capability of the IT equipment under extreme load conditions. And the actual range is where the facility and or the IT operator decide to operate their equipment and and is really going to be a balance between optimizing efficiency, total cost of ownership, addressing reliability issues, as well as improving performance. So a bit of history and the evolution of these guidelines. Prior to 2004, guidance on the allowable environmental envelope for IT equipment really varied from one manufacturer to another. So IT industry leaders started to talk about some sort of standardization, which eventually led to the formation of ASHRAE Technical Committee TC 9.9, which covers mission critical facilities, data centers, technology spaces, and electronic equipment. So in 2004, the first guidelines were released with the goal of really setting a standard and aligning ITE manufacturers to maintain equipment reliability. Power and efficiency were not a focus at this time. And you can see here that the initial recommended range is shown on the psych chart, and it's actually quite small, 20 to 25 degrees C with a relative humidity of 40 to 55% RH. And since its inception in 2004, these guidelines have evolved, and we'll cover those briefly here. So the next update to the guideline was in 2008, and one of the biggest changes in the second edition was the expansion of the recommended range in a desire to achieve higher data center efficiency at a lower total cost of ownership. So here we see a change in the recommended temperature range to 18 to 27 degrees C, as well as the addition of dew point to the humidity limits. There were no changes made to the allowable ranges in this update, but this is really when ITE manufacturers and data center operators started to move away from the notion that colder is better, and that by increasing the recommended temperature and humidity ranges, allowed for an increased opportunity to use compressor-less cooling solutions and economizer systems. The next update was then in 2011 with the addition of allowable ranges being added, and classes 1 through 4 were renamed A1 to A4 and B and C. Now this new guidelines was developed allowing data centers to operate in the most energy efficient mode while still maintaining the required reliability. So the addition of the allowable ranges A3 and A4 were created to achieve the most flexibility in the operation of the data center and really opened the potential for the use of free cooling systems in many of the world's climates. Now, the 4th and 5th editions were released in 2015 and 2021, respectively, with relatively minimal changes compared to the previous updates. So in 2015, the minimum allowable relative humidity limit was lowered to 8% after ASHRAE funded research showed minimal impact on electrostatic discharge induced damage. And then in 2021, the upper allowable relative humidity limit was actually adjusted to be dependent on the level of gaseous pollutants in the airstream. And there was also an additional high density environmental class that was added. So now that we've looked at the ASHRAE recommended and allowable ranges, I want to take a few minutes here and look at how evaporative cooling can be used to complement an economizer system to deliver these conditions more efficiently than a traditional mechanical cooling system. So we'll look at the psychrometrics on the next slide, but what we want to talk about here is evaporative cooling or adiabatic cooling process, and when we're referring to here is the evaporation of water into an airstream. So we're taking liquid water and we're converting it from its liquid state to its gaseous state. And in order to do this, it requires a certain amount of energy. The energy in this case is heat energy from the airstream, which is transferred to the water, resulting in a decrease in air temperature, as well as an increase in moisture content. So the main benefit to adiabatic cooling over traditional mechanical cooling is the ability to really provide a significant amount of cooling at an extremely low energy consumption. So the only energy that we're using here is already in the air. We're not using any additional mechanical cooling equipment. And to put this into perspective for you, to evaporate 1 kilogram of water requires 680 watts of energy. So that's the amount of energy that we need to drive that phase change from liquid water to gas. So that means for every 1 kilogram of water that we evaporate into the air, we can actually achieve 680 watts of cooling. Now, the caveat to this process is that the supplier does need an initial low humidity level to allow for that moisture to evaporate and provide the cooling. Because air can only hold a certain amount of moisture, if the moisture content or the humidity in the air is already high, it's going to limit the amount of evaporation and cooling that we can actually achieve with this type of system. So let's take a quick look at the process and what this looks like on the psychrometric chart. So I'm sure many of you are familiar with this chart, but we'll go quickly over the basic elements here. So at the bottom of the chart, we have the dry bulb temperature. We have the wet bulb temperatures going diagonally across the graph going left to right. We have the humidity curves going from right to left here. And then we have the absolute moisture content on the side of the graph. Now, from 2 of these parameters, we can actually derive several others. So if you have a dry bulb and say a wet bulb or a relative humidity or the moisture content, you can actually derive the specific enthalpy, which is shown on the sides of the chart here. So going diagonally along the left side and then along the bottom here as well. Now, specific enthalpy is actually a really key parameter for us when we start talking about evaporative or adiabatic products and the process, because the adiabatic process is a constant enthalpy process. So it follows lines of constant enthalpy. So if we know a starting position, we can actually plot that adiabatic process on the chart. So with that in mind, if we plot this out, if we have a starting temperature and humidity here, 40 degrees C at 10% relative humidity, we can actually plot the adiabatic process along that line of constant enthalpy. And you can see that we have a decrease in dry bulb temperature going from 40 to 18. And we also have an increase in moisture content as well. Now, this will be important when we start looking at how evaporative cooling can be used to achieve the desired supply air conditions to a data center or really any other application that you're looking at using this type of technology. And of course, it's the same with the Mollier diagrams as well. So we have our starting position at 40 degrees C, 5 grams moisture. %, relative humidity, following that line of constant enthalpy. Again, you can see we have a temperature decrease with an increase in moisture content or relative humidity all the way up to saturation. So when we look at the ASHRAE recommended and allowable ranges, we can see that by expanding out the acceptable operating range for a data center, we can increase the potential use for economizer and evaporative cooling. So if you have an outside air condition that's already within the acceptable range, you can potentially operate solely on economizer mode, bringing in outside air and using that to cool the data center. So if you have a condition here that's already potentially within the recommended or A1, A2, A3, A4 class range, you can simply bring in outside air and use that to cool the data center. Now, what we're showing here is if you have a condition, outside air condition or mixed air condition that actually falls within that blue region that we're showing on the screen here for any of these previous classes, we can achieve a supply air condition that actually falls within the recommended range all the way through A1 to A4 using an economizer combined with an evaporative cooling system. So if you remember that the adiabatic cooling process is a constant enthalpy process, we can determine our leaving condition simply by moving up that specific enthalpy line. Now, exactly how far up that enthalpy line you can go will depend on the capacity and the efficiency of the evaporative cooling system that's being used. And we'll talk about that a bit more when we start looking at the different technologies. So up until now, we've really talked about evaporative cooling for the use of cooling, but the other potential use case here is the benefit for evaporative cooling as humidification. Now, because evaporative cooling works through the evaporation of water, if you remember, as we cool that air, we also increase the moisture content or the relative humidity of the air. Now, the ASHRAE recommended and allowable humidity range is actually quite low. If you remember, it goes as low as about 8%. And in most places around the world, the outside air humidity for many times of the year will actually be above that. So no additional humidification is generally required. In our experience, even though the low end humidity is still 8%, we do still see designers looking to achieve a minimum of about 20% relative humidity. But again, this will be entirely dependent on the facility and where they decide to operate their equipment. So what we're showing here on the screen or on this map are the regions in blue. And in this case, it's areas where we would experience temperatures below 32 degrees or 0 degrees, 32 degrees Fahrenheit or 0 degrees C. And looking for a supply air condition of 64 degrees Fahrenheit or 18 degrees C with a minimum humidity level of about 20%. So if we were to simply take that outside air, that really cold outside air, and heat that without any additional humidification, we'd likely be well below that 20% minimum. So we'd need some sort of supplemental humidification. We've got a really great case study that shows this, and we'll talk about that later in the webinar. But the main point here is that if we have really cold air outside and we want to bring that into a data center, as soon as we heat that up, the relative humidity will drop, likely below that acceptable limit. So always consider additional potential humidification systems if you're in this type of scenario. So we've looked at the ASHRAE operating windows and how evaporative cooling can be used to help achieve them. What I'd like to do now is move into the different evaporative or adiabatic strategies and how they can be applied within an air handling unit or plenum or a duct. And we'll look at direct versus indirect evaporative cooling, as well as the strategy for direct humidification as well that we talked about. And for each of these case studies, we'll also look at how these systems are typically configured, as well as look at for each of these strategies, we'll look at how these systems are typically configured, as well as a live case study for each showcasing the energy savings that have been achieved using these evaporative strategies. So we'll start with the most basic here, a direct evaporative cooling system. So in this case, we're taking fresh outside air. We're going to run that through a filter, then through an evaporative or adiabatic cooling system. So we're evaporating water into the air, resulting in a decrease in dry bulb temperature, as well as an increase in relative humidity, and that air supplied directly to the space. On the other side, we've got return air coming from the space, and that's simply exhausted out. Now, key here is that we are going to be supplying that treated air, that cooled and humidified air, directly to the space. So any of that moisture that we're putting in to achieve that cooling is actually going to end up in the space as well. Now, there are ways to take advantage of the adiabatic cooling effect without adding moisture to the supply air stream, and we'll touch on that later when we talk about indirect evaporative cooling strategies. Now, the benefits with this type of system are that it can deliver a significant amount of cooling, as we talked about, 680 watts per kilogram of water evaporated, as well as the potential for humidification in winter months. So with this type of system, however, there are going to be some limitations. It does typically require high ventilation rates in order to maintain that cooling capacity, and it's not really suitable for humid climates where that evaporation is going to be limited. So the strategy is really ideal for hot, dry climates where the air can hold more moisture. And then, of course, the other consideration here for this type of system is, of course, filtration. For data centers, it's important to keep that outside particulate from entering the space. So filtration is always going to be a consideration when you're using a direct evaporative cooling system or strategy. So our case study for this strategy is actually from a UK-based AHU manufacturer called Weatherite. The objective here was to replace 30 kilowatt compressor-driven cooling systems with a refrigerant-free, energy-efficient solution for low to medium heat density telecoms rooms for one of the leading telecoms providers throughout the UK. And one of the main design requirements here was that the footprint for these systems needed to match that of the existing DX cooling systems so they could easily be retrofitted, and they wanted to use direct evaporative cooling. So here we worked with Weatherite to develop the evaporative system for this design. And this is a really great example because it shows that evaporative cooling can still be an energy efficient and economical solution on small scales or smaller systems as well. So you don't need to be deploying evaporative cooling on a hyperscale level to really see the benefits. So as we've talked about previously with economizers, evaporative cooling isn't always going to be required, and a lot of the time cooling can be done simply using fresh outside air or the outside air conditions. So how the system works is there are two operating modes. Mode 1 is called free cooling mode, and that's with the bypass damper open. So we'll go through the unit here. So mode 1, free cooling mode. At the top of the unit, we have recirculating air and a damper that, when open, allows for that air to be recirculated, mixed with fresh air, or when it's closed, can be used to exhaust air to the outside. On the right side, we have our fresh air supply coming from the rear of the unit that goes through a set of filters and then down through the bypass damper. So when cooling demand can be satisfied with circulating air, fresh air, or a combination or mixture of the two, those can be supplied down through the supply air grill that you can see at the bottom here and supplied directly into the space. So in this unit, or in the photo here, you can see the evaporative system, and that in this case, it's a glass fiber media system, which is activated when the demand cannot be satisfied using outside air only, and evaporative cooling is required. So in this case, we actually move into mode 2. So what happens here is the bypass damper closes, which forces the outside air through the evaporative media. We're going to have that media fully saturated with water. It's going to evaporate that water. We're going to cool and humidify the air. This can be mixed with recirculating air if required, and then supplied out the bottom of the unit. Now for the evaporative system, it is a recirculating evaporative system. So if you look at the photo, we do have a small sump in the bottom there, and then we do have an individual or single pump that's used to pump water to the top of the media. We'll continually recirculate that, and then we'll periodically drain that out in order to maintain a specific water quality. And that really helps just to optimize the water efficiency of the evaporative system itself. So you can see overall, just a very simple system. But what does that actually mean for the overall efficiency of the adiabatic system compared to the previous DX cooling system? So we've got a lot of data here on this screen, but we'll break it down for you. So on the left side, we have the ambient air temperature in degrees Celsius going from -5 up to 35 degrees C. The next column over, we've got the hours out of the year that will experience those ambient air temperatures. So we can see how many hours we'll experience those temperatures throughout the year and how many hours we'd potentially require cooling. Now the two next sets of data represent the performance data for the 30 kilowatt adiabatic unit compared to the legacy 30 kilowatt DX system. Now if we look at the ambient outside air condition and the associated operating mode, we can see that at about 15 degrees C or below, both systems, the DX system and the adiabatic system, would be operating in free cooling mode 1, or free cooling mode 1 only. So that's bringing in fresh outside air and putting that directly into the space. You can see the absorbed power on the next column, and they're not really that different. We've got 1.589 for the adiabatic unit, 2.45 for the DX cooling unit. We do see a slight decrease on the adiabatic unit, and that's primarily from more efficient fan motor and fan blades, but relatively relatively close together in terms of power consumption. Now, the change really occurs above 15 degrees C when we start moving into the 20 degrees C range, when we need to move into adiabatic cooling mode or evaporative cooling mode on the adiabatic unit, or DX cooling mode on the legacy system. So you can see that above 20 degrees C, our adiabatic unit goes from 1.589 to 1.66 kilowatts of absorbed power. And really that increase is because we've got to push the air through the evaporative media, so there's going to be a bit more power required from the fans, but still relatively close together, going from free cooling mode to adiabatic mode. Now, if you compare that to the legacy DX cooling unit, going from free cooling to DX cooling mode, you can see a significant increase here. So we're going from 2.45 kilowatts all the way up to 23 kilowatts. So a huge difference there on the DX cooling unit. And when we calculate out the effect or the cumulative effect of the run hours between both systems, the 30 kilowatt DX system compared to the adiabatic, the DX system would be using about 70,814 kilowatts throughout the year, compared to 14,088 kilowatts throughout the year. So a huge reduction in energy consumption between the two systems. So this table compares the energy usage between both designs. And as you can see, when we're experiencing the higher air temperatures going from 15 to 20 degrees C, there's a big jump on the DX cooling system compared to the adiabatic that stays relatively low throughout the year. So on the side, we've got the kilowatts per year. On the bottom, we've got the ambient air temperatures. You can note that they're not that different, below about 15 degrees C, but as soon as we hit that higher air temp at 20 degrees C, a significant increase in power consumption on the DX cooling system. So that equates to about an 80% reduction in energy consumption by moving to a direct evaporative cooling system from the traditional DX cooling system that was being used previously. So, huge savings, especially when we're considering that there are hundreds of these units that are out in the field. So overall, really, really successful project. So with that, we'll move into the other strategy that we'll talk about here. So that was direct evaporative cooling. But what if we had a case where we don't want the relative humidity, where we want to take advantage of the cooling, but we don't want that increase in relative humidity to make its way into the space. So in this case, the other method of applying these technologies would be through an indirect evaporative cooling system and the use of a heat exchanger. So in this case, we're taking our fresh air stream, which is cooled adiabatically, as close to saturation as possible, so the highest moisture content and the lowest possible temperature. And because we don't want that moisture to be supplied to the space, we'll actually use a heat exchanger like we would a traditional coil. So we'll pass the air through one side, we'll pass the cool air through one side of the heat exchanger, and then we'll just exhaust that out. Then on the other side, we've got our return air from the space going through the heat exchanger, cooling the air sensibly, and then supplied back into the space. So the same concept as if we were to use a coil. However, instead of using chilled water supply to cool the coil, we're using an evaporatively cooled air supply to cool that heat exchanger. So in applications where you don't want the air streams to mix, such as a secured building, this would be an ideal strategy. And the amount of cooling can be increased simply by circulating more air. And of course, we're not adding moisture to the airstream, and we're only sensibly cooling that through the heat exchanger. Another benefit with the strategy is that you're not limited to the extraction of the fresh air rates like we would be with a direct evaporative cooling system. And generally, this type of system will have a higher cost compared to a direct evaporative cooling system, and the efficiency will depend on the efficiency of the heat exchanger or the heat recovery unit as well. So let's look at a case study that utilizes an indirect evaporative cooling strategy. So this project is the Cork Internet Exchange in Ireland, and the objective here was to provide cooling to a newly built data hall using air-to-air and evaporative cooling technologies only. They did not want to use any DX expansion cooling systems, so no chillers or mechanical cooling in this type of system. So we worked with a leading air handler unit manufacturer to supply the evaporative systems for this project. So we'll take a look at the schematic here first. I'll do a bit of an explanation here. So this is a schematic of the air handling unit that was designed for the data hall, and we'll go through this stage by stage to see what's happening. So if we draw a line straight down through the building, each side is mirrored, so there are four circuits of airflow in this system. So we've got the left side and we've got the right side. So starting on the left, we have outside air that's drawn through an evaporative cooler, where of course, if it's needed, we'll evaporate the water into the air, resulting in a decrease in temperature and an increase in humidity. That goes into a mixing area where it can be mixed with exhaust air, depending on the controls and if it's needed. That air then goes down through a damper over a pair of heat exchangers. So you can see go through heat exchanger 1, through heat exchanger 2, and then can be exhausted out or returned back into that mixing area. On the other side of the heat exchangers, we've got air coming from the hot aisle, and that splits to the left and to the right because it's a mirrored design. Going through heat exchanger 1 where it's cooled sensibly, going through the second heat exchanger where it's further cooled sensibly, and then down into the cold aisle. And then from there, it's recirculated back through and continually just recirculated through the system. So I just wanted to explain that before we start drawing in. We've got an animation here, so it can get a little bit busy, but I'll hit play so we can go through that again. So we've got the outside air coming in, evaporatively cooled through the 2 heat exchangers, and then exhausted out. Then on the other side, we've got hot air coming from the hot aisle, going through the first heat exchanger, through the second heat exchanger, down into the cold aisle, and then just continually recirculated. So again, just like having a cooling coil, we're taking warm air and cooling it sensibly and putting that back into the space. Only in this case, we're using an evaporatively cooled heat exchanger instead of a chilled water coil. So this is what the system looks like, and just to give you guys an idea for scale, you can see a small step ladder there beside the unit. Air is drawn up. If we look at this again, air is drawn up from the hot aisle, through the first heat exchanger, through the second heat exchanger, and then down back into the cold aisle. And then on the other side, we've got the evaporatively cooled air coming through the first heat exchanger at the top, through the second one, and then exhausted out through the top. And then here you can see some additional photos of the air handling unit. Again, quite an impressive design. So when we looked at the power demand for the unit, we were of course using free air cooling whenever possible. So when the ambient air temperatures were lower, we had a moderate power demand since we were just running fans. So you can see here, the orange or yellow line here is the power demand with the temperature range along the bottom. You can see that when we start getting into the higher ambient air temperatures, we start diverting or putting air through the evaporative coolers. So our power demand does increase. So you can see kind of above this, kind of around 16 up to 20, we start seeing the evaporative coolers activated and power demand start increasing. Or what I want to point out here is if you look at the actual power demand, we max out at about 25 kilowatts to operate the system, but we are delivering 400 kilowatts of cooling. So a huge amount of cooling for a significantly low amount of energy input to the system. So some additional details on this project. We had 4 400 kilowatt modules installed. Return air was 40 degrees C coming from the hot aisle. The supply air temp was 26 degrees C, and the heat exchanger efficiency was about 80%. The electrical consumption per 400 kilowatt module was between 11 and 25 kilowatts, with an actual average annual power consumption of about 12 kilowatts, which in the end gave us a power utilization efficiency, or PUE, of less than about 1.4. So this, compared to the legacy design, resulted in a reduction in energy of about 75%. So again, a significant amount of energy saved in this application by using an indirect evaporative cooling strategy. So now we're going to look at our final strategy here, which is using evaporative technologies to increase humidity without necessarily using it for the objective of cooling. So as we saw earlier, when we looked at the world map, this type of humidification is very beneficial when used alongside free air cooling systems in colder regions, where without any proactive moisture addition to the system, the indoor relative humidity would likely be extremely low. So benefits with this type of system are, of course, very low energy humidification if used with heat recovery, high capacity humidification with very little energy input. So just to give you an idea, 200 pounds of humidification done through a more traditional electric steam system or an isothermal system would require about 75 kilowatts of electricity. When we look at this with our evaporative system, which can actually deliver about 2,200 pounds an hour of humidification, would consume less than 0.3 kilowatts of electricity. So ideal for cold climates and applications where waste heat is available and it can be used for cooling as well. In terms of limitations, there are, of course, a few here that we do need to talk about. So you may not need that cooling effect. So if you're looking for humidification, but you don't need the cooling, one of the things that you do need to consider is the potential need to preheat the air in order to offset that cooling effect that we get with the evaporation of the water. So of course, really ideal if you've got an application where you need humidification and cooling at the same time with waste heat available. If you don't have that waste heat available and you don't need the cooling, you would potentially need to look at preheating that air before it goes through the evaporative cooler. The other limitation here, when we start moving into cold water, adiabatic, or evaporative systems for humidification, is of course the hygiene consideration. So limitations on the hygiene side are typically a bit more stringent compared to an isothermal system where we're boiling the water, really killing anything that's in that water that's being used for humidification. Whereas with an evaporative system, you may have potential concerns over bacteria and hygiene of that water quality because we're not boiling that water. So the case study that we have for you here is a meta data center located in Luleå, Sweden. And the objective was to maintain a minimum humidity level across a large data center located just outside the Arctic Circle while operating solely on a free air cooling strategy. So the humidity range for this design was that kind of 20 to 80%. And given the climate in this part of Sweden can drop as low as minus 40 degrees C, once that air is introduced into the building, heated back up, the indoor humidity would likely drop potentially as low as about 2%. So without any proactive humidification, we'd be well below that minimum 20% limit. So humidity control was a necessity here. And of course, with the massive air volumes, evaporative humidification with that preheat available, using hot aisle from the data halls was really an economic and efficient solution. So here we worked with Kundal, the consulting engineer, and Bravida, the contractor to supply the evaporative cooling systems for this project. So here we can see a schematic of the system, which in this project is referred to as a penthouse ventilation system. Each section is referred to as a lineup, and there were 13 lineups per data hall, with 2 data halls in this building in particular. And a lineup consisted of the intake and return air mixing plenums, filter section, the humidifier, the supply fans, the relief fans, and then dedicated controls controlling everything. So you can see on the right side, we have the outside air, dampers bringing in fresh outside air. We've got hot air coming back from the space where it's mixed in the mixing plenum with the cooler outside air. That mixed air then goes through a set of filters. And then you can see our evaporative modules here, consisting of a glass fiber media with a water recirculation or pumping system. That humidified air is then supplied down into the data hall, and then on the left side, we've got our exhaust air plenums. So here you can see some actual photos of the evaporative systems. On the left side in both images, you can see the evaporative media. And then the second image, where we've got on the first image, the filter section with the green filters here. And then on the second image, we've got the fans on the opposite side of the humidifiers. In this case, the humidifiers were actually full walls of evaporative media, double stacked, spanning across the entire plenum. So a couple more images here. The image on the left, you can see the evaporative media system. Turn the lights off here. You can see a slight glow coming from the bottom of the sumps, and that's actually the UV water sterilization system that we implemented here. You know, we talked about hygiene for these types of systems, and UV treatment is a really common hygiene control method used in evaporative cooling systems. And then the other image here on the right just shows the air supply into the data halls. So some project specifics here. Supply air temperature range was 18 to 29 degrees C with a humidity range of 20 to 80%. Outside air temperatures ranged from -40 to 30 degrees C with temperatures very rarely rising above kind of that 30 degrees C mark. However, in this case, we could potentially use the evaporative systems for cooling as well. Fresh air rates range from 18% at -40 degrees C all the way up to 100% when the ambient air temperatures were less than 18 degrees C. And we supplied 52 evaporative systems with a max humidification load of about 11,700 kilograms per hour and a total humidifier power consumption of only 32 kilowatts. So you can see with the size of this system, we were able to supply a significant amount of humidification with very, very little energy use required from the humidifiers themselves. And again, there was no mechanical cooling system installed here, resulting in an overall PUE of around 1.07. Now, if you were to compare, the power consumption for the evaporative systems to, say, an electric system or electric humidification system, the evaporative system would represent or use 99.7% less energy. So huge potential savings from the humidification side. So we've looked at the ASHRAE environmental envelopes and how evaporative cooling can help to achieve supply air conditions within those ranges, along with the strategies and how they can be implemented. So now I just want to take a closer look at the actual adiabatic technologies that are available in the market today. So these will include your more traditional evaporative media systems. We've got included in there high pressure atomizing systems, a unique hybrid system, and then we'll also touch on chiller pre-cooling with adiabatic technologies as well. Now, for the sake of time, I won't go in depth on each of these technologies, but we do have a number of other webinars and blog posts and information available online that cover these in detail. A lot of the webinars are already pre-recorded if you missed them and available online, so feel free to check those out on our website. So the first technology that we'll look at here is an evaporative media system. This is also known as a wetted media or wetted pad system, evaporative cooler, wet wall, or you may have even heard this referred to as a swamp cooler before. And this is really the most common type of adiabatic system in data centers. So how it works is it's typically sized to match the internal dimensions of the air handling unit or the duct or the plenum, and we can have actually multiple units installed like we saw with the Meta case study. Air is pushed through an evaporative medium. In this case, it's a glass fiber matrix. Now there are other materials available for that matrix within these types of systems, but generally glass fiber is the most common for data center applications simply due to the flame or fire and smoke ratings. There will be a water supply and typically a pump system So when we have a demand for cooling or humidification, the water supply will start filling the sump at the bottom, and then we'll start pumping water over the media. Water then cascades down over the media, eventually fully saturating it. And as air passes through the media, a portion of that water is evaporated into the air, which of course gives us that decrease in dry bulb temperature and increase in relative humidity. Now, one of the main benefits to this technology over some of the other ones is that we do not need any type of water treatment with this type of system. Because all the evaporation takes place within the depth of the media itself, any of the minerals that are in the water that will potentially precipitate out as a result of that evaporation will either get flushed out or will start to form a scale on the media. Now, to help with that scale formation or scale buildup and water quality within the system, these will typically have some sort of bleed cycle controlled through a water conductivity sensor or a timer. Now, water quality, cycles of concentration, scale formation, media life, those are all in-depth topics. We can probably talk another hour or two on those. But if you are interested in learning more about that and how water quality affects media on these types of systems, we've got some really great blog articles available on our website as well. So just a couple considerations here when you're looking at an evaporative media system will be the media velocity and the typical control accuracy. So the media velocity, or the velocity onto the media, will have an impact on the efficiency of the system. So when we talked about that that enthalpy line and how far up that enthalpy line we can go, this is where that comes into play. So it's the efficiency of the evaporative system. How much water can we evaporate into the air? Now, because the evaporation takes place within the depth of the pad, it comes down to the contact time between the air and the water. So if we have a really high velocity, we end up lowering the contact time between the air and the water, which results in a lower evaporation efficiency. The other potential issue with velocity is if it's too high, there's potentially a risk of that air pulling water off of the media, forming droplets that can make their way into the section downstream. So these systems are typically designed around a media velocity of 3.5 meters per second, or about 700 feet per minute. And then the other consideration that we talked about here is controllability. Now, because the media will take time to fully wet and dry, there's going to be a ramp up time and ramp down time that needs to be considered. So in order to help with this, systems will typically have some sort of staging available where we stage or wet only certain sections of media depending on the output required from the system. So in general, with these types of systems, control accuracy will be in the range of plus or minus 10%. Next technology that we'll look at is a high pressure atomizing system. So this works a bit differently in that we are actively spraying water into the airstream where it's evaporated. Now, because we're spraying the water into the air, we do need to use treated water, such as reverse osmosis, which will actually pull out or remove 95 to 98% of the minerals. The problem is if we don't remove those would potentially clog the nozzles and precipitate out as a dust, which can make their way downstream and potentially into the space. So how this works is we have a pump station that will pressurize the water to about 1,000 psi or 70 bar. It's passed through a set of control valves into an nozzle manifold where it's sprayed into the duct or the air handler. Now, the efficiency here will depend again on velocity and that absorption distance, again really coming down to the contact time between the air and the water. The distance here inside the air handler will typically have a nozzle grid along with some sort of droplet separator, mist eliminator downstream. That distance is generally 5 feet or about 1.5 meters as a minimum. And that really determines the efficiency of the system. The control accuracy with this type of system is generally better than an evaporative system, in the range of plus or minus 5%, which is achieved using a series of valves. And those valves that we can see here mounted on the side of the air handler are going to be connected to a different number of nozzles for each valve. And by operating or turning on a specific combination of those valves, we can vary the output from the system. The next technology that we'll look at here is a combination of the last two, which is actually a fairly unique system, Condair. It's what we call a hybrid or DL system. And in this case, we're spraying water into the airstream. So it does, again, still need to be treated with reverse osmosis. And then downstream, instead of a droplet separator, we have an evaporative media, which in this case is a porous ceramic media, which acts as both a droplet separator and a post evaporator. And with this combination, what that allows us to do is actually shrink that installation length or absorption distance from 5 feet or 1.5 meters that we would typically need with a high pressure system down to 2 to 3 feet or under about 1 meter. So we still have, if you look at the schematic here, we still have the water treatment system, which is supplying a hydraulic module, does operate at slightly lower pressure, around 100 psi or 7 bar. We do include multiple valves for staging, as well as a hygiene system here, and then that feeds a nozzle array inside of the air handler. So staging here is achieved in a similar way to a high pressure system, with each valve connected to a different number of nozzles. But what's different here is we also have the ability to increase the pressure to the nozzles with an optional pump, which gives us even tighter control, somewhere in the range of plus or minus 2% control accuracy with this type of system. So when we compare the three technologies, there's 5 main comparison points. We generally look at water consumption, energy consumption, pressure drop, control tolerance, and of course the air handling installation requirements. So when we look at the evaporative media system, water consumption is going to be relatively low, typically 1.1 to 1.2 times the evaporation rate, which includes the flush cycles, because you can use mains water, so we don't need to use RO. Energy consumption is relatively low, generally less than 0.5 kilowatts per system. Pressure drop will be slightly higher since we do have to push that air through a thicker evaporative media. And of course, the control accuracy that we talked about in the range of plus or minus 10%. Big difference here is the air handler material can be standard since all of the evaporation takes place within the depth of the pad itself. With a high pressure system, water consumption is going to be higher because we do need to use reverse osmosis water. So with the typical RO system, 50% of the water that's going into the RO system will be rejected out. So we do need to consider that in the overall water consumption for the evaporative or adiabatic system. Energy consumption is still relatively low at less than 1 kilowatt. Pressure drop will be lower compared to the evaporative media system, since we'll have a thinner droplet separator, and the air handling material does need to be stainless steel for the length of that absorption distance. With the hybrid system, water consumption is going to be medium because we do still need that reverse osmosis water, but the evaporation efficiency that we have will be slightly higher compared to the HP system because we've got that additional ceramic media downstream. Pressure drop will be a little bit higher since we, again, do have that ceramic media that the air needs to be forced through, but the control accuracy is a bit better at plus or minus 2%. And of course, the air handler material does again need to be stainless steel, but can be a shorter section compared to the high pressure system that we looked at. So as a final technology or really application that I want to touch on briefly here is pre-cooling using an adiabatic or evaporative system. So there's been a lot of talk in the industry now about the transition from air cooling and evaporative cooling towards liquid cooling. And I think that the landscape for liquid cooling is yet to be defined, especially at a large scale, but it is evolving quickly. So what I want to point out here is that even in a liquid cooled system, whether it's a liquid to air cooling system or a liquid to liquid cooling system, there's still going to be some sort of heat rejection equipment. And that heat rejection equipment can still benefit from evaporative cooling. So for example, if we talk about air-cooled chillers, what we're seeing is a demand for evaporative pre-cooling to help pre-cool the supply air onto the chiller. So as ambient air temperatures begin to rise, existing chillers that are installed in the field may struggle to keep up. Or if you're designing around peak design days now, which may only happen 20 to 30 hours out of the year, you may potentially have to look at upsizing your chillers. Whereas with an evaporative cooling system can help is by cooling that air adiabatically on those extreme days, your chillers can still operate within their design range, and it can potentially help reduce the overall load on the cooling system as well. So the most common technologies that we see here are evaporative media systems or atomizing or nozzle systems, and a lot of the manufacturers do offer this as a standard. And there are also products that can be used to retrofit existing installations as well. So just to wrap up here, I'd like to take a couple seconds here and just talk about some of the additional services that we offer at Condair. So in addition to offering all of the technologies that we talked about here today, we do have an extensive service offering available as well. So we offer installation and preventive maintenance across all of our products. On the media side, we offer something called the KEEP program, which is a more data and metric driven approach to help you decide when and if your media needs to be replaced. And we do offer full wet section maintenance as well as media changeout service as well. And then of course on the engineering side, we can help with psychrometric analysis to help determine the performance of an evaporative cooler in your design. And of course, if you're unsure whether evaporative cooling would even make sense in your application, we can certainly help evaluate that as well. And then finally, we do offer media scaling analysis, which can help with site selection, particularly with the water quality that's available on site and how it could potentially impact media life. And then, of course, system design if you have very specific needs or requirements or specifications for any of your evaporative or adiabatic systems. So I know that was a lot of information to fit into an hour here, but that is the webinar for today. I think Dave will open it up to some questions.
Sorry, Will, have we still got you there?
Yep. Can you hear me, Dave?
Okay, we seem to have... Oh, I can hear you, Will. That's much better.
Oh,
Will,
okay.
thank you so much for the presentation. Lots of information there. We do have a number of questions, if you're okay, just for a couple of minutes.
Yeah, absolutely.
Will, when using evaporative media, what water quality is acceptable, and can grey water be used?
Yeah, that's a really great question here. We know that water quality is always a big topic with any type of adiabatic system, and when we start talking about data center applications, the amount of water that we're using comes into discussion as well. Generally, for water quality with adiabatic systems, our general rule of thumb is if you can drink the water, you can put it into an adiabatic system or an evaporative system. Generally, with an atomizing system, we do need to treat it with RO. What we are seeing a lot of these days, at least here in North America, is the use of reclaimed or recycled water. So water that's not quite drinking water quality, that is available from the municipality, but is used for evaporative cooling systems. So water quality, again, always a huge discussion. Generally, the main concern with water quality from our side is going to be a hygiene aspect. But when we're talking about evaporative systems, the minerals and what's in that water will actually come into play when we start talking about media life as well. So if you do have questions about specific water qualities, feel free to reach out and we can always help. As I mentioned, we do have the ability to look at that and provide scaling analysis inputs on water quality being used for specific evaporative media systems.
Brilliant, thank you, Will. We did have another question come in. So this presentation has not covered Legionnaire's disease. Is this a concern that can be covered?
Yep, that another really great point. In terms of Legionnaire's disease and hygiene, I know kind of the standards and requirements in Europe are right now a lot more stringent than what we've got here in North America. I know ASHRAE has put out standards regarding water management systems when you're using evaporative cooling or cold water systems. We don't cover that specifically here in this presentation. Dave, I don't know if we have anything that covers that that you've done previously. Sorry, Dave, I think I might have lost you there.
Yeah, we did. Sorry, Will, I was just wrapping up the webinar then, and we thought we'd lost you for good there, my friend.
No.
So with that, we'll draw the webinar to a close, and again, thank you everybody for attending.
Perfect. Thanks, everyone. Really appreciate it. Appreciate your time.
Okay, thanks, Will.